Okay. So for information, I will draw on whiteboard here. So example 2 just now. You expose your metal inside carbon dioxide and you put your sample inside the oven and you pump in the CO2 inside. This process is called carburizing process. So what you do, you infuse CO2 carbon inside on the metal. So what they do is carbon bond into the metals here, and you're given the diffusion rate. The D actually is how the penetration of the carbon can be. So in this question, you're given the depth surface 5 mm depth. So 5 mm from the surface of your burner is 1.2 when it's reached by 10 mm is here. So it's like the same as you plot graph C versus X. So you have two values there, 5 and 10 mm. So 5 we have 1.8, 10 we have 0.8. So we have a graph. Okay. So here is y equal to mx plus c. So same like k equal to minus d dx. We see dx. So this is the gradient of this point. Right. So how you find your m? The graph y2 minus y1, x2 minus x1. Okay, so that's why we can answer your x2 so you find the gradient. And you continue. Atomic diffusion, non-steady state, already done with the steady state just now. Now we go into non-steady state. It is happened in the normal operation. Non-steady states, they are independence of times. So Frick's give you second law. First law apply to steady states. Second law, diffusion, they give you this equation. C T equal to dx over dc dx. So on the left hand side is the rate of composition change in x direction or in the thickness over time. On the right hand side is diffusion multiplied by the rate of change of concentration of the gradient. Okay, so this different. This happened in the non-steady states on Frick's second law. So the two equations, don't confuse between the previous one and the previous one is a steady state. Second one is a non-steady state. Okay, so I skip the derivation for solving this differential equation. Let's go directly material something. So some textbook they use the partial differential sign. See this partial differential. It's the same that we derive from this partial differential section. So you're given the x solid A, solid B. So A go into B at location X. So as time diffuse increase, so more solute will go inside the solid. It's going to go inside the solid. And what case that diffusion can happen? Two factors that you need to remember. One, there must be empty particles or values. Second, there must be enough energy for it to penetrate or go inside of the stage. These are the two main ideas of the diffusion. So it gives you the diagram. So how you read this graph? In initial, nothing happened. You start with initial concentration C0. You start at T equals 0. But when you have A and S, so if diffusion of gas A will be independence of position, then solution to Fick's second law is what? So this is more popular than the first rules, and this one, okay. So you use Cs minus Cx divided by the difference of the initial, and ERF bracket x over 2 divided by d3. This one you need to refer to the table to apply this rules. So there is another writing for second rules, second law. You can write as Cx minus Co divided by Cx minus Co minus 1 over Ef or something. It's the same thing where you take the ratio of CO, you change the top one divided by CO, then you will get this equation. It's the same. It's the same. Either you use CS minus Cx or CS minus CO. But if you use CO, the second one, remember the right hand side is 1 minus. It's a rearrange of equation. So in test, you can use either one. Test or final exam, you can use either one to solve. CS is a surface concentration in the gas diffused into the surface. CO is before initial case. Cx is the one distance that you want to find. You apply this one only for non-steady state diffusion. Non-steady state diffusion, or if you see the question mentioned, Fick's second law means it's a non-steady state. ERF is an error function, which is being read from a table. By this table, okay. Is a long table, it's a simplified one. So how to read this table? You read from one column Z and the ERF Z, 0 to 3.5 continue to Z, ERF 0.4 to 0.8, then continue to the next one and so on. Okay. So this one is like statistics installments. We know that the statistic table, so same like statistics, but it's a distribution table. Okay. Now example 3 is a demonstration how you apply the apple. So let's say you have a gas categorizing the same one. The one that you see on the whiteboard here is the first case, the first law. Second, example 3 is non-steady states. So categorizing a gear of 102 steel at 927 C Celsius or Fahrenheit. Calculate the time in minutes necessary to increase the carbon content from 0.4 at 0.5 mm below the surface. Assume carbon content at the surface is 0.9% and the steel has a nominal carbon content 0.3. Given that diffusion coefficient is 6. Now, how do you know that you need to apply this one? How do you know? You will see, it will tell you concentration of the surface. Okay. It will ask you, it will tell you, assume carbon content or certain element of content at surface is so much. Then you know that you need to. You didn't see it in the first rules. The first rules just tell you the depth, and what depth, what percentage, what depth, what percentage. That is 676. This one, you apply CS minus CX divided by CS minus 0 equal to ERF bracket X divided by 2 square root of P of T. Okay. Now, if you remember this structure, and I'll show you the table, right? So RF Z is this value, Z is this Z. So when you find the value, don't confuse with the table. So you have CS surface 0.9%, original is 0.2. CO is original. Tell you still have a nominal carbon content before you do the curing, already have 0.2%. So CO is 0. Okay. Now CX here is what you want to find. To tell you calculate the time necessary to decrease carbon content from 0 to 0.4. Means 0.2% up to 0.4 at this depth. Okay. So to help you illustrate or help you to visualize. Let's say you have a flat surface. So I do the cross section. So it treated at 927 C. The carbon content you need to find at this X. The carbon content you must reach 4%. Surface 0.2% at surface. Okay. So surface is 90%. 0.9. Okay. Then the nominal carbon inside the carbon already have 0.2%. So it asks you to find the time for the carbon content of 0.2 reach 0.4 at a certain distance. 0.5 mm. Okay. So you plug into the equation here. X divided by 2 square root of dt. Okay. So X we have 0.5, CX 0.4, target is 0.4, original is 0.2, surface is 0.9. Okay. So remember to convert everything into ASI, which is indicator. The diffusion is given 1.28. So the only missing is a time difference. Right? We have a CS, CX, C0. So you calculate the left-hand side first. Right? Substitute. You know your left-hand side value, right? Your left-hand side value is what? ERFZ, right? ERFZ. So don't confuse with the value here. So here is from the paper. This whole thing is ERFZ. Don't confuse that. This one is Z. This is Z. This side is ERFZ. So you read from the table. So 0.7143. So you read the table, ERF 0.743 on the table. So just now, you calculate 0.7143 is your ERF Z. Go and find this way. Don't go and find that. This value is ERF Z. So where is this one? 0.71 is about here. So here to here. Right. The skill set here is to apply your interpolation history. And if you don't know what is interpolation, go to us. We go to teach you how to do interpolation. Okay, so you'll find a value here 0.17143. You find what is your ER value. So 0.7143, you find what is the exact value. Okay, once you find your exact value, substitute back here. Then you find it. So, okay. So the careless mistakes usually I see in a test or final exam, students confuse between these two. They read the wrong value. Okay, so there you do interpolation, you find what is your x. Your exact value is 0.755. Substitute back here, find it. Okay, the key is 8, 5, 6, 7 seconds. The question asks you how many minutes. Convert this one into minutes. Okay. Okay. This is example 3. Are you able to solve this question? If you understand question 3, you should be able to solve this one. I'll give you the question again. So consider a gas vaporizing again here at 927 degrees C as in example 2, same. But this problem calculate the carbon content at 0.5 and predict the surface of the gear after 5 hours of vaporizing time. Assume that the carbon content at the surface is 0.9 and the steel have nominal carbon of 0.2%. Give you the D same value 1.28. So what is the carbon content and 5 units? Which one is missing? This equation, which parameter is missing? Parameter. Do we have CS? Yes. Yes. Do we have CX? This is the one you need to find. CO, you have a X, you have a X is what? Okay, convert to meter. D is given to meter. T is given 5 hours into 200 seconds. 5 times 3,600. Right? Times 60 times 60. Right? So only one missing there. The challenges is don't read the wrong value. In this case, in example 3, you have this value. This example, you have this value. So what is the value over here? What is the value? Okay, what is the value? What is ERF X divided by 2G? What is the value? What is your ERF? What is this? And 9.6 or do the X cos line. What is the value inside? 0.52, 0.52, 3 or 1. This is the value. Agree? Yeah. Before I go there, I go to your show you the data. Where is ERF 0.5, 0.521? 0.5, 0.15. You are ready to have. Yeah. Yes. Yeah. No. 0.5 and 0.51. Yeah. Yeah. Yes. You reading this one? Yes. Yes. Okay. So you know what is your PRM integration? Yeah. It's about 0.554. Do integration. Is that? Yeah. PRM or what's not right? 0.5, 0.55. So just now you are giving 0.521 here. So you don't know about this one, right? With the pressure 0.5205, 0.5623. You don't know this one. Or find this one. Right? You do it question. Okay, good. You know how to pick the number. Okay, I show you the example is 0.56423. Okay, so you know the value from the paper because you are missing these values. Right? So you from the table is here, right? It's the one that same like one more. Do interpolation, we find your ERFZ equal to 0.538, about 0.54. Right? Then you substitute back. Okay. Substitute back. Okay. Substitute back, you're able to find your CX. This value is what you find this now. Yeah, just below them, between them, about there, about there. But if you see the table is four decimal, please find 4 decimal. Okay, about there, about there. Because the value is substituted maybe use 2 or 3 decimals. You understand that? Important you understand why cross multiply, right? You can say cross multiply. Okay, so like the one I show you here is the integration step. I don't know your interpretation that let's share this one. The one is I use 0.5 and size. This one you need to compare. You need to compare this one and this one and this one is cross. Right. And you take this one minus this one. Depends how you do your calculation, but I'm showing you my way. Okay, so don't read the wrong Z and the other. Important is these steps. So once you understand, you're clear. So what does it mean? It means that at a certain x 0.5 mm, your x will reach below 0.52% after exposed to 5 hours. Right? So you compare example 3 and example 4. There is information there. So this one will read the PowerPoint slides. Right. Now example 5. Example 5, what is the difference between the previous one? What is the difference between example 4 and what do you see the concentration unit? Concentration now become atom over vacuum. Just now, what? 2%, 0.2%, and so on. So This read number 5. He asks you if gallium diffused into silicon wafer with this is a chip, so with no previous gallium at temperature so and so for 3 hours. What is the depth below the surface at the concentration of this one? If the surface concentration is this one, given by this one. So we do the same, but now the concentration is atom over meter cube. Same thing, but we do the same procedure. Only need to be careful on that unit. Because CS, you know, CS is given. Cx, but you know the target location is this one. C0. C0. You're not given, so it's 0. So if we tell you what, consider the impurity diffusion of a gallium into silicon wafer. So if you know how they make silicon wafer, they don't allow impurity before the process. Put it in the vacuum. So at the surface, they should not have any impurity. So don't say, sir, I don't see any surface concentration like that. You need to see how they ask you question. This is called purity. You don't want purity normally. Okay, so the concentration at the surface or initial is 0.1. Because this is a silicon wafer process, we don't want impurity before we start on the surface. It's a very clean surface. Right? So the rest you substitute. This case X is missing, B is given, time is given, and we find the left-hand side. Left-hand side means you find this value to refer to the ERF value, ERZ value, then you find out what is it. Okay, different. The skill set here is reading the paper. So this one is reading. Take the paper and find. Okay, the rest I go very fast. This is for the information. How diffusion happens in the industry. So this is for case hardening of steel, impurity doping of silicon wafer that you see in the example now. Right. So it's a common process to make things harder. For example, the gear. Right? Gear in your machine. Right? So you see the carbon surface, so we have the top view. If you drive car, needs the spot ring and all this to go through this process. Case carburizing. 2 minutes.
Hi, I'm Mike Santora, Associate Editor for Design World Magazine, and today I am with Prime Metals Technologies Mechanical Engineer and Manager of Bearings, John Bacher. John, thanks for having me today.
Thanks for having me, Mike.
Okay, so today we're going to talk about case carburization. John, what is case carburization and why do we need it for our bearings?
Well, in relation to bearings that have case carburization, this is a through section of an inner race. As you can see here, the darkness spots around the outside, those are hardness spots. And basically, this allows it to have a wear surface, but keep a ductile base material on the inside, so it'll handle shock really well. So in an application like a tapered roller bearing, where you see both axial and radial loading, it works really well.
And so, John, what's the process like for case carburizing?
It's a number of different heat treat processes. They stick it in an atmosphere. They do a carburizing process where they add the carbon into the metal, and that's what gives it its depth. You know, for certain applications it's deeper, and for some it's really thin, depending on how the bearing's used. And then they do basically a quench and temper, which gives it its hardness to bearing hardness, which is usually about 58 to 60 Rockwell.
And what do we have over here?
This is a through hardened example. Basically, what's interesting about this is you can see the dark layers all the way through. Now you'll lose a couple of points of hardness from the outside to the very center, but basically all your cylindrical, your spherical bearings are this material here. And what's interesting about this is the reason why you use this for a tapered roller bearing application. You use
So impurity doping, silicon wafer, this one there's a video over here. So how they make silicon wafer?
Humble sand. This is what the building blocks of the future are made of. But making them is a long process comprising a great many steps. First, the silicon dioxide in the sand has to be converted into pure silicon. After that, it is cut into wafer-thin discs. In Dresden, these raw wafers are 300 millimeters in diameter and less than a millimeter thick. In our clean room, up to 35,000 chips are then made from each of these discs. In numerous process stages, the wafers are given their characteristic surface structure. After coating with a photoresist layer, the wafer surface is exposed, developed, and etched. This results in the desired conductor structure. Such structures are hundreds of times finer than a human hair. Dopants are then implanted in the material to increase the electrical connectivity of parts of the semiconductor. In subsequent phases, this and other process steps are repeated until the entire layout of the chip has been deposited on the wafer. This involves heating the wafer to more than 1100 degrees Celsius, in some cases up to 27 times. Up to 200 measurements are done, and up to 26 exposures. All in all, this can mean as many as 700 processing steps and 14 weeks processing time. Once this is completed, the microchip is assembled from as many as 30 such layers, like a mini skyscraper. Each layer has its own function. Interconnecting them makes the microchip highly complex. Semiconductor chips, the building blocks of our future.
So this is asynchronous diffusion. V equal to DOE minus Q divided by RT. So if the question asks you the diffusion, then you need to use that. So this is just a direct application. Too simple, sometimes you can ask this. So it's a linear function. V equal to DO and exponential Q divided by. So how we apply? Find the value of B in meter square per second for diffusion carbon alpha in gamma at certain degree. Use DO equals something, Q equal to something, R equal to something. Then you just solve. So we substitute DO is given. E exponential, Q is given, R T is given. What is need to be careful here is to change your temperature into Kelvin. And the value is solar. So again, everything that you link with the exponential E, you can write in a log or log same time. So we read. So there's a table that I showed you just now. Yeah, either in table or in the plot. This one you can find in the encyclopedia of material, or especially when you work in the silicon industry, or those are high-tech industry, especially in the R&D department. You will see this. So these three reported by experiment, or you can find in the encyclopedia. Okay. So this one by experiment, just substitute the value. So diffusion of silicon atoms in atoms, diffusion D is given and temperature is one, and a certain temperature is this one. So you have two D. D, the first D is with 500 degrees C, second D is 1000 degrees C. Calculate the activation energy release Q for AG and the temperature range 500. So you do the Arrhenius type equation. D equal to D. So this basically you do the ratio or interpolation. Right? So just substitute and then you find the relationship between the two. You're able to solve for the Q. Means you put the Arrhenius 1 and 2 equation together, you ratio it, then you're able to find the missing temperature. Sorry, the missing Q. So by using table below, compute diffusion coefficient for magnesium in aluminium at 500 degrees C. This is also a bonus question. This question, if you ask you to find diffusion coefficient, a certain material, then you just go to the table of diffusion. For example, this case, example 8, magnesium in aluminium. Magnesium in aluminium. So you go to the table, magnesium, species, diffusion, magnesium, host metal is aluminium. So you go to the table, find the row and column. In this case, you have the DO 1.2, activation energy 1.3, and the T and D is over here. So here is 550 degrees C. The table here is 500. So you need to do interpolation. So here, your D value is 1.2 kilo from here. Here. E exponential, Q given 1.3. Kilojoule, again, kilojoule, change the K into 10 power 3. R is 8.31 constant value. T, remember to change to Kelvin. 550 Celsius to Kelvin. So this is how you do. Design question. This one is your homework. Go and read up. This is your test standard. And test standard, this is your homework. If there any question, all the answer is there. If there any question, come and ask. Okay. So, all the answer is there. So with this, we conclude chapter 5. All the answer is there. Go and read up. Then these are the example of question that will come out. All right. You can try out. One.